We are back once again. It is day 98. Yesterday, we went through the crucible, the furnace, the land of suffering. We did a weekly contest. It actually wasn't suffering. I'm going to be honest, it was actually kind of fun. So I think we'll do it again. We got the tip to do it from Thomas, so I don't see why not. We could just do it every week. So I think I have to pick my time properly, though, so that I can do it when everyone else is doing it. So then I'll actually try and like race with everyone. So I'll try that. So we'll try and do that next Sunday or Saturday. So whenever they do that. But I'm also realizing, got a comment yesterday from T Wong the God, if my YouTube loads, but it basically just said, oh yeah, he said, I guess you should switch to languages or just completely don't use something like Q and do this question with DFS. I'm actually not certain how you would do this question with DFS because I see it as a native breadth first search solution. But I think we got stuck since we were using a Q. We're getting n squared on the we're getting n squared on the shift operation, which I think was just killing our time. But I actually did some research, and it turns out that LeetCode for all the environments of the programming languages does include some special additions to languages, so you don't have to recode them. So I think for our use cases, we'll just try and use it for this problem. So there is a Ruby deck that is actually included. So we're going to try and use that one to see if our original solution even works or holds up. And then if it does, perfect. If not, that would be unfortunate. But yeah, I would say that's what we're going to do. And then we're going to try and finish up the remainder of the contest. And then we're going to jump into some easies. We're a bit strapped for time today. So I'm actually just going to jump into it to start. And for some reason, you can't actually see my timer. So you cannot see my timer, which is a little bit frustrating. I guess streaming on Windows is just not an awesome experience. I gotta be honest. Not a great experience. But it is what it is. You can't see the timer. We're gonna do an hour for today. So we're just going to do that, and then we're going to see if we can pretty much finish this Ruby deck version of the weekly contest, and then we'll start doing the weekly contest regularly. So that's what we're going to try and do. And so let's just jump into it. So you're working on a problem called reverse odd levels of a binary tree. We copied in an implementation of a deck that was just not good. So I think what we can do up here is, I think we can just include algorithms. No, I think it's looks like it is require algorithms, and then in the algorithms namespace, I think we can include containers. So this should, oh, it's gonna give us an error because we removed a bunch of things. But now when we create our deck, we can actually just do Ruby deck new, which we should be allowed to do. Oh, actually it is just called deck. So I think we're actually fine there. And it doesn't take anything. Actually, we could give it something to start, but we'll keep it as it is now. We do have push back, right? And the error we're getting is value.value. So maybe we don't have to do this stuff anymore. Maybe we can just shove this backwards like this, remove this end statement, and I'll make this slightly bigger since actually it's a little bit hard to follow. So it looks like it's working again. 7, 11, 13. Let's try with the example test cases. Your answer, expected answer. So this one seems even slower. So, maybe our problem is not the queue. Maybe our problem is not the deck. So we actually still get TLE. I don't understand them. I guess people are saying, Thomas said he used DFS. I guess I didn't even explain the premise of the problem, but we're given a problem, right? It's called reverse odd levels of a binary tree. We're given a binary tree. We want to reverse the values of the nodes for every odd level of the binary tree, where the root node is actually level 0. So if you had DFS, I understand how it would work for this first case here, because you're just going to swap these two. But at this case, when you have these two nodes, what would you want to do next? You'd want to swap this node with this node, and this node with this node. But then here you want to swap this one with this one, this one with this one, this one with this one. Then you would go right, then you'd go left. You'd swap this one, this one, and this one, this one. So I guess you could do DFS, but I just don't understand. It's a little frustrating that BFS doesn't work when I feel like it. I don't see why it shouldn't. TLE. and curl level dot each do node. I'm wondering if it's this portion right here that is giving us an issue. We can just check, honestly, when we get TLE, we'll just say puts curl level dot length. There's a lot of work to do, I'm not gonna lie. Oh wait, I think I see what's happening. If we process every node in a level and then iterate over it, no, that would just be 2n. We'll just visit the entire tree twice technically. So what if we do just scrap it? What if we scrap it and just do BFS? I think we could make DFS work. But yeah, it's just really sad. I just don't understand why this one is so slow. And maybe we should just let it go and move on, but that's hard. Is it the reverse unshift? I think that could also be it. What if we just switch reverse as well to deck.new? We have reverse.shift. We'll change that to pop front. And then do we have a clear method? We do. So here we want to clear, so we'll just say reverse.clear. And unshift, we pretty much want to add it to the front. So we'll just say push front. Or is it unshift? We'll say push front. And I think we're having the same issue here because we were doing unshift, which is also n squared. Puts curve dot length. I think if I remove this version is much slower. It's very interesting though, because when I was using just the native array, which apparently is optimized to be able to use like a deck anyway, it was actually faster. That's sad. Yeah, I think we just have to switch. I think it's just sad though. I really want to know why. Really want to know why the DFS or BFS doesn't work. We're using a deck for both dig and review. About it reversed. There's another thing we could do. Since the tree is perfect, this might be controversial. I'm going to switch to TypeScript because I think that would be the fastest way to do this. This might be a controversial method. What we could do is turn the actual tree into an array of values, and then from there you can actually just calculate the odd levels. So if you want the odd level starting at, for example, this tree, is there no dark mode for LeetCode? Or do it in light mode, I guess, today, because I can't see the tree. So what we could do, right, if we want to get the one level, right, we could just do the level that we want, right, which would be here. So the 1th level would be 1, and then we want 1, 2, 3, which would be the next odd level, which would be 3, and 3 would actually be, I think, starting at this list of 1s here is where 3 would actually be. Right, so if we have 0, because we know how many nodes, since the tree is perfect, we know how many nodes a tree, we know exactly the next number. Actually, no, yeah, we know the exact, it's a perfect binary tree, so we know for each line the exact number of the next number of nodes. So we want to start the first value in every level. If we want to start at level 1, we just go to level 1, right? And if we wanted to get to 0, which starts at index 0, 1, 2, 3, right, we would do 3 times 3, and then we have 1 here, which starts at 0, 1, 2, 3, 4, 5, 6, 7. Times 2 minus 1. We want the 3rd level, we do 3rd level times 2. We have 1, 2, 4, 8, 16, 32. So we'd have the level, which is 3. We want to map it to the index, which is this 0 here. We map 0, 0, 1, 2, 0, 1, 2, 0, 1, 2, 3. So it's this 3rd index here. This 3rd index here, we want to map to the 4th index. So to get the 3rd level, or to get the 2nd level, because yeah, this would be, I keep forgetting, this is level 0, this would be 1, this would be 2. So to get the 2nd level, All right, the second level maps to this index here. So 2 times 1. So it'll give us 3. So maybe if we try that for here, 1 starts basically 4, 5, 6, 7. So you want the third level be 2 times the level plus 1. Which would give us 8. So let's see if this works. If we wanted to get the level 0, it'd be 2 times 1, or 2 times, I forgot it was the level times 2 plus 1. So it doesn't really work for the first root, which is fine. For 3, right, we want to get the index where 3 would start. We would say 3 times, maybe this only works after that. So if we wanted to get index of 8, level 8 would be 3. I think we did this before and it only worked after a certain amount. So if you wanted to get this index here for 12, this index here for 12, 12 maps to 0, 1, 2, 3, 4, 5, 6, 7. Index 7, right? We want to get the level starting at 4. Four times In fact, I think we don't need to actually figure out an equation for this. I think what we could literally just do is just turn it into an array of values. Since the tree is perfect, we can just skip ahead based on a specific amount of them. So I think the whole thing would be the tree to array. And then I think we can move this back to night mode. So the goal would be tree to array, use array to reverse values. To turn the tree into array, we could just do a BFS, which looks like that is the order that they're using. So right now they just have it in level order. So we could just do that. So we'll just create a function to array. It's going to take a tree node you start and it's going to return an a tree node array. And we'll say const array is going to be equal to array root, and then we'll say console.log array, and in here we'll use in here we're going to use a queue, which is going to give us n squared time on this anyway, but maybe we'll pass, we shall see. Right, and the queue is going to start with the node in it, and then we're going to have our array, which is what we actually return. And then we're going to say while queue.length does not equal 0, right? We're going to say node equals queue.shift. So we're going to try and take a node off the front of the queue. All right, if the node exists, which actually I think we're guaranteed to exist because it's a perfect binary tree until we reach the leaf at the end, for which we wouldn't add anything onto the array for. But we're just going to do r.push node, and then here we'll say if node.left, right, queue.push node.left's value, and then we can duplicate this. We're gonna push node.right, and I think we should get the array that we're looking for with this. So we're given a binary tree like 7, right? We start with the root node 7 in the queue. While the queue isn't empty, the queue isn't empty, so we pull off 7, we push 7 onto the array, right? And then node.left and right exists, we push 13 and 11 onto the array, onto the queue. Then the queue isn't empty because it has 2 values in it. So then we do node.left. Then we pull it off the front. We'll take 11, it exists. So r.push 11, right? Its left node doesn't exist, its right node doesn't exist, and the queue isn't empty, so we go to 13, we push 13 on to the array, and it doesn't have a left or a right child. So let's see what we get. Line 32. I think it's upset that we're not. What happened to the closing bracket down here? We're just going to return null. Line 39, car 1. Maybe there's something I'm missing down here. So say use example test cases, and I'll just take the smallest one to start. Run it again. Seven, 13, 11. So this is perfect. It comes out looking like an array because I think they have a special toString function on the tree nodes that make them print everything they're attached to. But I think we're just good if we work on node.val. And then I think here we could just swap the node values. So the goal here would be we have an array of these node values now. So the first level would be 7, and then the next level would be 13 and 11 together. Swap those values. So I think we could do that. As we start, the problem is we start at node 1. We want to work with the second level. Start at node 1 or node 0 or node 1, but it's the 0 with level. We want to work with the odd levels. Odd levels. We want to work with the odd levels. We want to work with the odd levels. This is what we currently have. I think where I'm stuck, I'm not stuck, but where I think I'm messing up or I'm getting a little confused, we're starting at the first node, and we want to use the odd level. We're going to process the odd level starting at that node. But how do we know what level we're at? We'll start at level 0. At level 0, we have to process at least 2 nodes. And then we go to the next level. Should be 1. And then we go to the next level, which would be 2. If we go to the next level, which would be 2, which would be here, that's actually 0, 1, 2, 3, 4. Two times the level. And then if you wanted to go to the second one here, which would actually be level 4, 0, 1, 2, 3, which would be level 3, a 1 would start here. The node is 0, 1, 2, 3, 4, 5, 6, 7. I think we can just write this out. So level 0 starts at index 0. L1 starts at what index? 1 starts at index 0, 1, 2, 3. And then L2 starts at index 0, 1. No, L1 starts at index 1. then L2 starts at index 3. So L2 starts at this first one, which is 0, 1, 2, 3. And then L4 starts at 0, 1, 2, 3, 4, 5, 6, 7. One has 2 nodes, level 2 has 4 nodes, and level 3 has 8 nodes. So it looks like for each level, the function to get the node or the index where that level starts is just level it looks like it's just the number of nodes at that level minus 1. Is equal number of nodes at level minus 1. So how do we know the number of nodes at a level? I think it's just 2 to the level. I see now. I think yeah, it's 2 to the n minus 1. I think. Because even for level 0, 2 to the n, which is 0, is 1. Minus 1 would give you 0. So if we did a for loop and we set let I equal to 1, which is the first odd number, we'll do I plus equal 2, and actually it might just be easier to just say, oh no, yeah, I plus equal 2 and I is less than array.length, right? And this is really just the level, so we'll just call it L, or where the levels start. No, actually, it is just the level. It is just level, so we don't actually want to do while is less than array.length. Actually, it's actually easier if we just use a while loop. So if you just say level start index is less than array.length, and we'll say let level start IDX starts at 0. Actually, it's going to start at 1. And so starting at index 1, we're going to want to swap the values in that, reverse the values in that range. So we want to know the number of nodes for that level. it's going to be level, or it's going to be 2 to the level, or 2 to the level want to know the number of nodes at level 1. Level 1 has 2 nodes. Oh, it's just going to be 2 to the level, actually. And then minus 1. To get the next level to start, we're just going to do, like, if we wanted to start at this level 3, we have to be at the level before us, and we'll just say 2 to the level minus 1 plus 1, I think would give us the starting index. We already have a variable called starting index. Num nodes is equal to 2 to the level. I think I see where the issue is. This gives us the number of nodes at a level. And to get to the next one, we're going to have to already start at the base level. So if we start at level 1, which is here, to get to the next level start IDX. We start here, starting at level 2 here, level 1. Then we just want to get to here. We just add first we do our work, and then we do, so I think I see what I'm getting confused. We're gonna have node index is less than array length and level, which is 1. Now when we have the node index, which is 1, right, which is gonna be here, we're gonna do our work, and then we want to go to index 0, 1, 2, 3. Now to do that, I think all we should have to do is just add the number of nodes at this level to the value. So we'll say do work, and then node index plus equal num nodes, and then we can just say level plus equal 1. So I think if we print node index and level, So at level 1, the starting node, at level 1, the index for that node would be 1, which is true, right? And at level 2, our starting index for that level should be index 3. So at level 2, this would be 0, 1, 2. Our starting index would be 0, 1, 2, 3, which does work. And for level 3, our starting node would be 7. So 0, 1, 2, 3. Our starting node would be index 7. So 0, 1, 2, 3, 4, 5, 6, 7. So that does work. And so I think all we should have to do now is just swap the nodes. But I'm pretty certain this is the same speed as the other one. So it was still worth it, I guess. So now we just need to swap the values, right? We can just do like a string reversal function, right? So we can just do is say let left equal node index, and then we'll let right equal node index plus, right? If we're at the 4th level or 3rd level, 0, 1, 2, 3, and our start index is 7, right? 0, 1, 2, 3, 0, 1, 2, 3, 4, 6, 7. We have 8 nodes here. So 1, 2, 3, 4, 5, 6. So I think it would just be node index plus 2 to the so 15, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I think this works. So we're going to do -1 because 15 is out of bounds. And then we just want to say while left is less than right. All right, we're just going to swap the values. So we're going to say temp going to be equal to, what is it? You can call it array sub left dot val, and then we're going to say array sub left dot val equals array sub right dot val, and then array sub right dot val equals temp, and then we'll do, this is just like the string, it's like reversing a string, so we'll do left plus equal 1 and right minus equal 1. And then I think we should be able to return root. So it doesn't quite work. It works for these bottom 2 cases, but we're just off. We do 2, 5, 3. And then we want to swap the values here. 8, 13, 21, 34. Wait a second. It says 8, 13, 21, 34. If you reverse the values at this level, you get 34, 21, 8, 13. Oh god, I forgot the odd levels part. So that's my bad. I forgot that part. If level mod 2 does not equal 0, or we can just do it like this. If level mod 2 does not equal 0. So that was my bad. I just forgot. Then we're just going to shift all this up. So let's try submitting it, see if we run out of time. So this does seem to work, which is a little bit disappointing. A little bit. I think my Mars is probably the slowest solution. I can't even see where the bar is, but if we're at 653, I think we're actually the high score of the slowest possible version. I feel like if we did the deck version here, because we're doing we end up doing yeah, and even the way we're using the Q here is n squared time. So yeah, I think there is a quick library we can use for JavaScript. There actually is not. Yeah, I guess that's why people say use Python, because you get so many data structures for free, and C++ as well. I didn't realize it would be such a problem. Maybe we'll start using Python as well for these problems where like we need access to these specific data structures. But yeah, it's slightly disappointing just because we had to do a lot of extra stuff just to. Yeah, so that is unfortunate, but I'm also fairly certain that the BFS based Ruby version would also work if I just changed it really quick. So I'm going to copy this whole thing, and I'm going to bring it into TypeScript. We're going to reset the code. Okay, it didn't even copy in the slightest. Oof. And if we go into TypeScript, I think, bro, why can't, oof. Oof, oof, oof. So maybe now we can finally just copy it normally. Okay, so now I think if we just convert this to and we're just going to use a bunch of this whole thing should be pretty slow, but I'm pretty certain it should work at least a little bit. Q.pop front becomes shift. This becomes equals null. It's a const n. What does n even mean? Oh, bro, the bindings are so messed up. My page is just refreshed, and now my coding window is gone. We're just gonna wrap it up there, I think. So, we're gonna try and do the last problem tomorrow. I'm a little. It sucks that the odd levels of binary tree version didn't work, but or it looks like it removed. Maybe I have to go. All right, so it looks like we have some of prefix score strings remaining. And this one looks like a hard, so oof, oof, oof. So we'll try this one tomorrow, but we shall see. Yeah, and I would say that is a wrap for today.